Okay, let's just dive right into this. In our previous explainers, we spent a good chunk of time laying down the ground rules for linear time invariant systems. You know, LTI systems, as we love to call them. We've talked about linearity, we explored causality, and we've unpacked time invariance. But now it is time to introduce one of the absolutely most powerful and honestly beautiful mathematical tools you'll ever use for representing these systems. I'm talking about the transfer function. Because let's face it, we engineers absolutely despise doing complex calculus by hand. So if you want to truly understand how a system behaves without pulling all your hair out, this right here is your master key. But before we get to the solution, we kind of have to talk about the problem, right? How exactly do we go about simplifying complex system dynamics? Because if you've ever tried to model a physical system, whether that's an electrical circuit, maybe a mechanical suspension, or even a chemical reactor, you know that things get very messy very fast. We are constantly dealing with time domain calculus. We've got rates of change, slopes, accelerations, and it all just piles up into these massive, complex differential equations. So what we're really searching for today is an elegant, almost secret mathematical escape route. We want an insider way to bypass the heavy lifting of calculus and turn our system analysis into something, well, much more manageable. So here is our transformation roadmap for today's explainer. Think of it as a journey. We start out with a really complicated differential equation in the time domain. Then we use the Laplace transform as our vehicle, basically a bridge, to cross over into a completely different mathematical space. And finally, we arrive at our destination, the transfer function. We call it g of p. This super compact representation takes all of that complex LTI input-output dynamic stuff and just packages it neatly. So let's break down exactly how we take this journey. To appreciate the cure, we really first have to understand the disease. And our mathematical villain in this story is the time domain differential equation. Whenever we look at a system in real time, the relationship between what goes in and what comes out is heavily governed by derivatives. And let's be real here, trying to directly solve or manipulate high-order derivatives in the time domain is just exhausting. It's computationally heavy, it's totally unintuitive for complex systems, and it makes combining multiple systems together an absolute nightmare. Let's look at the anatomy of that villain for a second. We have a general input-output differential equation in the time domain, which is our starting point. Look at how perfectly it's divided up. On one side, we have everything relating to the output, y of t, and its various derivatives up to the nth order. On the other side, we have everything relating to the input, u of t, and its derivatives up to the nth order. And those constant coefficients you see, those just represent our system's physical parameters. You know, things like mass, resistance, or maybe spring stiffness. It's a mathematically precise relationship for sure, but again, solving this directly with all those nasty derivative terms is exactly what we are trying to avoid. So how do we escape? Well, we need a runway to take off into a simpler mathematical domain. And that runway is built on one absolutely crucial assumption: zero initial conditions. This simply means we're assuming our system starts completely at rest. Zero stored energy, no initial charge on a capacitor, no initial velocity on a moving mass before our input is actually applied. By setting these initial conditions to zero, we completely clear the path to use our ultimate mathematical shortcut. Enter the hero of our story, the Laplace transform. Fun fact here, Pierre-Simon Laplace didn't even invent this for engineering. He originally used it for probability and celestial mechanics. But for us, under those zero initial conditions we just talked about, the Laplace transform does something pretty magical. It takes the derivative of a function, which is a really complex calculus operation, and turns it into simple algebraic multiplication. Specifically, an nth-order time derivative literally just becomes the variable p raised to the power of n. So we apply this transform to both sides of our messy time domain equation. And suddenly, all those difficult derivative terms, they vanish. They are entirely replaced by powers of p. Our lowercase time variables become uppercase Laplace variables. We have officially left the time domain and entered the p domain. The calculus has been completely converted into basic algebra. Okay, so the really crucial point is what we can actually do with this new algebraic equation. Because it is just algebra now, we can rearrange it. We can group all the output terms on one side, all the input terms on the other, and simply divide them. And boom, that gives us the transfer function. It's the official definition, the ratio of the output to the input in the Laplace domain, assuming zero initial conditions. Notice how it forms this nice rational polynomial. The top is made entirely of the coefficients from our input side, and the bottom is made of the coefficients from our output side. We have literally taken an entire system's dynamics and compacted it into a single elegant fraction. But let's just pause for a quick second. Math for the sake of math is fun and all, but we are analyzing real physical systems here. We have this algebraic fraction, but what does it actually tell us? How do we extract physical, structural meaning from a polynomial fraction? Like, how does looking at this equation tell us if a bridge is going to wobble, or if an amplifier is going to screech, or if a robot arm will move smoothly to its target? Well, to answer that, we just have to factorize our equation. By factoring the top and the bottom, we reveal two highly critical features, zeros and poles. The terms on top are the zeros. When p equals one of these values, the whole transfer function just goes to 0. We plot these on the complex plane as little open circles. But the real stars of the show here are the terms in the denominator, the poles. If p equals one of these pole values, the denominator becomes 0, which means our entire transfer function shoots straight off to infinity. We plot poles as little x marks on the complex plane. And I really want you to remember this. Poles strongly, heavily influence the system dynamics and stability. Where these marks land on the grid completely dictates how the system behaves over time. We'll be exploring that deeply in the future. But for now, just think of the denominator as the system's DNA. Now, looking at this incredibly clean block diagram in the P domain, if we want to find our output, all we have to do is take our input and multiply it by our transfer function. That's it. Simple multiplication. But here's a super fascinating thought experiment for you. What if our input is a sudden, infinite spike of energy, an impulse? Well, the Laplace transform of an impulse is simply the number 1. So if our input becomes 1, and we plug that into our equation, our output exactly equals our transfer function. This means the transfer function is literally the Laplace transform of the system's impulse response. The math just lines up perfectly. So let's take a quick breath and recap the incredible logical chain we just built today. We started with a serious problem, the tangled, complex differential equation. To rescue ourselves, we assumed 0 initial conditions and deployed the Laplace transform. That magically transformed our calculus into algebra, which allowed us to derive the transfer function, a super compact, powerful ratio of output to input. Finally, we factorized that function to reveal the poles and zeros, laying bare the absolute structural core of our system's behavior. It's just a highly satisfying, elegant escape from mathematical complexity. But this is really only the beginning. If the denominator is the system's DNA, what happens when we decide to play genetic engineer? What happens when we force those poles into new positions to control a system's destiny? Well, next time, we're going to dive into stability and frequency response, and we'll start charting these behaviors visually with Bode plots. If this explainer helped clear up the journey from differential equations to transfer functions for you, please go ahead and like and subscribe so you don't miss the rest of this series. And hey, I would genuinely love to hear from you. Drop a comment below if there's a specific step, formula, or concept from today you'd like us to unpack in more detail. See you in the next explainer.